Hello everybody, I'd like to go through a few problems involving differentiation of algebraic expressions. But before I do that, let me just do a brief recap quickly of some of the rules. So when we're dealing with let's say a function of the form f of x is equal to ax to the power n. Well, the derivative, which we can write as f prime of x, that apostrophe is f prime, or we could also write it df dx. So this d over dx is like an operator of sorts. It's a differential operator. And the general rule is we bring the exponent down, so it's n times, keep the coefficient as is, x, and then the power of x is reduced by 1, so it becomes n minus 1. And this rule applies for n negative as well, and even n as a fraction. So basically it applies for all real n. And this is very nice. So there's some rules. So if we had two functions, f and g, for example, so the derivative, let's say d dx of, I'll use square brackets here, of f of x plus or minus, same rule for minus, g of x. The differential operator just acts on each one. So it's just df dx plus or minus dg dx. The product rule, which involves multiplication, of course, is a little bit different. So let's just be careful here. So I'm going to drop the x there. I'm just going to write fg. So this one here works like this. It becomes the derivative of the first function, so it's df dx, times g plus f times the derivative of g. And of course these things can be proven by first principles, but I'm not going to do first principles in this video because that's going to be a separate video. So we're not going to prove anything yet. It's just rewriting the rules so that we know when we have to use them. So the quotient rule, which is division, this is now when the function f is divided by g. This one's a bit ugly. So what happens is it's df dx times g minus f dg dx, and all over g squared. So this one is quite brutal. But sometimes you can just use the product rule. Maybe I should put the names of the rules here. This is product rule. And then this is the quotient rule. So this is just a brief, I'm just putting this here for reminders so that when we actually do the exercises. So sometimes you can, multiplication and division are inverses of each other. So you could, if you want to avoid the quotient rule, you could do the product rule, but with f times 1 over g, for example. And then comes the most important one here, and sometimes the most challenging, is the chain rule. The chain rule is when you have a composite function. So for example, if you've got d dx of f of g of x, this is known as a composite function. So with the chain rule, we want to get the derivative of the outer function df dg times dg dx. So I know this might feel a bit abstract, but we'll see it when we look at an example. The alternative notation we can use is f of g of x, and then if we want the derivative of this, let's use prime. It becomes the derivative of f prime of g of x times the derivative of g of x. And both of these are equivalent. This is the chain rule. When doing problems with the chain rule, think of f as the outer function and g as the inner function. And then what you end up doing is that you take the derivative of the outer function, So if we had something like x squared plus 1 or cubed, for example, x squared plus 1 would be the inner function, and then the brackets cubed would be the outer function. So what you do is you take the derivative of the outer function, so that's just 3, and then everything in the bracket stays the same, and then the power of the outer function becomes 2 because it's 3 minus 1, and then you multiply it by the derivative of the inner function. So in this case it would be 2x. The inner function stays untouched, but we'll see it properly as we do more examples. So let's do the problems here. Let's start with question A. Here's a perfect example of using the chain rule. We've got the outer function, which is the square root, and then the inner function. So we could, let's first write this as x squared minus x plus 1 to the power a half. So according to the chain rule, so therefore I'm going to use dy dx notation. We bring down the half, keep the inner function untouched, reduce the power, so it's a half minus 1, you always minus 1, and now we multiply it by the derivative of the inner function. So the derivative of the inner function, well, x squared is just 2x, and then minus x is just minus 1, and the derivative of a constant is 0. And this is basically it, it's a simplification. So this is x squared minus x plus 1 to the power negative half, and then times 2x minus 1. And we don't like leaving our answers with negative exponents, so to change the exponent to a positive, we have to put it under the division line. So we end up finally with 2x minus 1 all over 2, and I'll write the square root again for the power half instead of writing the power half. Let's look at the next one, question B. So this one is going to involve the product rule. So let's rewrite this. So y is equal to, so of course you could always expand it out and do it term by term, which maybe we should do. So let's expand this. So we end up with x squared plus x squared over the root of x. Let's write the root of x as an exponent. So this is x squared plus x squared times x to the minus half, because remember it's in the bottom, it's underneath the division line. And then we have x squared plus, and we know that if you have two with the same base, if you multiply two the terms of the same base, you add the exponent. So the exponent here will be x to the power 2 minus a half is 1.5, which we write as 3 over 2. So now the derivative here is actually fairly straightforward. It's dy dx. The first term is just 2x, and then the bottom term here is 3 over 2 times x to the power 3 over 2 minus 1. Always remember to subtract. Maybe I should write explicitly on the first term as well. 2x to the power 2 minus 1. So this is just 2x to the power 1, we just ignore the 1, plus, and then 3 over 2 minus 2 is just a half, or 1 over 2. So this is 3 over 2 times x, 1 over 2. And if you want your final answer back with the square root there, we can do that. So we can have 2x plus 3 over 2. So once the differentiation is done, it just becomes a matter of simplifying. So looking at question C, again now you can see why things like the product rule comes in handy, because imagine we have to expand all this now. This would be tedious and very likely to make a mistake. So now we can use the product rule. So let's first break it down. So let's make this f of x. As you get better and practice more, you won't have to do this, break it all down like this. You can just do it straight. And then maybe it will be a good idea to get the derivatives of these first. So df dx would be, we take the power 4, we bring it down, keep the inner function untouched. This is the chain rule, but now we must reduce the power to 3. And now we must multiply by the derivative of the inner function. So 2x plus 4, the derivative is just 2. Because 4 is, the derivative of constant is 0. And then let's get the derivative of dx, the derivative of g. Well, that's just 3x minus 2, so that's just 3. And now if you do the product rule, it's not so bad. So y prime or dy dx. Let me just be consistent. Dy dx. And this is now, product rule is the derivative of f, which is 4 times 2x plus 4 all cubed times 2. And then we keep g, 3x minus 2. And then plus, now we keep f by itself. So this is just 2x plus 4 to the power 4. And now the derivative of g, which is just 3. And now again it's just simplification. So let's just try and see how nice we can simplify this. So the 4 times the 2 is an 8. So we end up with 8 2x plus 4 cubed times 3x minus 2 plus 3 times 2x plus 4 to the power 4. And if we really want to, we can factorize further. 2x plus 4 is cubed is actually a common term there. So we can factor it out. So we have 2x plus 4 all cubed. And now this goes into what? I'll use square bracket. 8 times 3x minus 2 plus 3 times 2x plus 4. And I'm sure we can even factorize further if you want to, but I don't think that's necessary now. Because the differentiation part is done. It will depend on the question, how far you want to factorize this. So d is s of t. We don't know what s is. It's a function of t. And this is t squared over 6 minus t. So this is a good candidate for the quotient rule. So let's again do this. Let's make this f of t. And let's make the bottom one g of t. And then using the quotient rule, ds dt will be df dt times g minus f times dg dt. I know I wrote this above, I'm just doing it again for my own sake as well. And then g squared. Alright, this is equal to, so the derivative of f is just 2t. T squared becomes 2t. And then g we leave it as is, so that's just 6 minus t. And then minus, now we take f, which is t squared. And then the derivative of g, so 6 minus t, only t gets differentiated, so it's minus t, it becomes minus 1. And then this is all over g squared, which is 6 minus t all squared. Now let's see if we can factorize a bit further here. If we expand here, we get 12t minus 2t squared plus t squared all over 6 minus t squared. If you just factorize a little bit further, we see there's 2t squares there. So negative 2t squared plus t squared is just 1t squared. Well, negative 1t squared. So we can write this as 12t minus t squared all over 6 minus t all squared. And we can factor that t if you want to, but again, it depends on the level that you want to factorize to. We can write this as 12 minus t times t. But I don't know if this is going to help anybody. So let's just do this one again quickly, but do it a bit different. So without using the quotient rule, you can use the product rule as well. You can do it like this. We can write s of t as t squared times 6 minus t to the power negative 1. Remember, If something is under the division line, it has a negative exponent. And now we can use the product rule instead of the quotient rule. So the first derivative of t squared becomes 2t, and then keep the second one untouched there, and then plus t squared. But now the derivative of 6 minus t to the minus 1 is minus 1. Keep the inner function the same, 6 minus t. Minus 1 is minus 2, so the power is minus 2. And then the inner derivative here is minus 1. So yeah, I use the product rule and the chain rule. Now we're just curious to see if we get the same answer. This is more complicated than the quotient rule in this example, but we should get the same answer. So let's see if we do. So the first term here on the left, I'm going to write it 2t over 6 minus t. Let me just put it in brackets anyway, just to the power 1. Plus, now is this plus? Well, we've got a negative 1 times a negative 1, so it is plus. Plus t squared all over 6 minus t squared. So if we want common denominators, we're going to have to multiply the term on the left by 6 minus t at the top and the bottom. So we end up with 2t times 6 minus t plus t squared all over. So this is just adding fractions. 6 minus t all squared. And if you simplify this, you get exactly the same answer as above. So you get 12t minus t squared over 6 minus t. So you can use the quotient rule or the product rule combined with the chain rule, whichever one is more comfortable. You get the same answer. So let's do this last example, which is y is equal to the square root of 2x minus 1 over 3x plus 1. So again, we have options here. We can write this as is equal to the square root of 2x minus 1 over the square root of 3x plus 1. And then we can do the quotient rule. We can write this as 2x minus 1 to the power half over 3x plus 1 to the power half. Let's identify this as f, and this is g, and let's just get the derivatives of these guys. So df dx, well, 2x minus 1 to the power half, so we bring the half down, the exponent, keep the inner function the same, reduce the exponent by 1, so half minus 1 is just minus a half, and then multiplied by the derivative of the inner function. So 2x minus 1, the derivative is just 2. The 2 and the halves cancel, and we're left with just 2x minus 1 to the power negative half. I'll leave it like this now because we are still going to simplify further afterwards. And then dg dx will be very similar. It's a half times 3x plus 1. Reduce the power by 1, so a half minus 1 is negative a half, and then times 3. And then this is 3 over 2, 3x plus 1 to the minus a half. So again, we want to use the quotient rule or the product and the chain rule. Let's go with the quotient rule. So I'm just going to write QR. So dy dx. I'm not going to rewrite what the quotient rule is. We should know now. So it's df dx, which I'm just going to write as 2x minus 1 to the minus a half, times g, the original g, 3x plus 1 to the half, then minus, keep f by itself, so 2x minus 1 to the power half, and now the derivative of g, which is 3 over 2 times 3x plus 1 to the power minus a half, and all of this must be over g squared, which is 3x plus 1 to the power half squared. Let me just do it to the half squared. And if we further simplify, well, this one's not very pretty, as you can see. But we have to simplify it. Let me break the terms apart. So we have 2x minus 1 to the power minus a half times 3x plus 1 to the power half over, so the half all squared becomes to the power 1. I don't think I closed this bracket here. 3x plus 1 minus 2x minus 1 to the power half times 3 over 2 3x plus 1 minus half. So this is quite messy. We have to be careful. And 3x plus 1, yeah. So to simplify this further, I would probably recommend writing the denominator as 3x plus 1 to the minus 1. So let's rewrite these terms. 2x minus 1 to the power minus a half times 3x plus 1 to the power half, and then times 3x plus 1 to the minus 1. So that's the guy that's being divided here. And then we do the same thing here, minus 2x minus 1 power positive half times 3 over 2 times 3x plus 1 to the power minus a half times 3x plus 1 to the power minus 1. And now we can just try and further simplify. So the first term remains 2x minus 1 to the power minus half, and then here 3x plus 1 to the power half times 3x plus 1 to the minus 1 becomes 3x plus 1 to the minus a half, and then the second term here is 3 over 2 2x minus 1 to the power half, but now this becomes 3x plus 1 to the power negative 3 over 2, because it's negative a half minus 1. We don't want negative exponents, so let's write these without negative exponents. So we put them underneath. This is the square root of 2x minus 1 times the square root of 3x plus 1, and then this term here is minus 3 times, this is a simplification. We're done with calculus. We've been done with calculus for a while actually. Most of this has just been algebraic manipulation here. And then this is 3x plus 1 to the power 3 over 2. It's a very ugly answer, but that is the correct answer. Alright, that's it for this video. Thanks guys, bye bye.